In the last lecture, we were analyzing forced convection in the flow around a particle at high Peclet number. So, the configuration was a particle of radius r. Incident on the particle is flow with a free stream velocity Vfs, and there was the particle was at temperature surface temperature T naught in a fluid in which the temperature was T infinity far from the particle. Okay. So, that was the configuration that we were trying to analyze. Okay. Now, in the limit of high Peclet number, okay, that is the Peclet number is Vfs into d by alpha, where alpha is the thermal diffusivity and Vfs is the free stream velocity and d is the particle diameter, 2 times the particle radius. In the limit of high Peclet number, there is diffusion from the surface because the temperature at the surface is higher than the temperature in the ambient fluid, and there is convection downstream. Okay. In this particular case, the convection is rapid because we know that the Peclet number is large. So, the strength of convection is large, and therefore, you would expect the disturbance to the temperature field to be restricted to a thin region close to the surface, okay, of thickness delta, okay, which is much smaller than the radius. We had analyzed this in a coordinate system in which x was the axis that was opposite to the free stream velocity. If this were a particle moving in a fluid, then x would be the direction of the particle velocity. In this particular case, we are sitting on the particle in a reference frame that is moving with the particle, and the flow is going past in the negative x direction. Spherical coordinate system, because this configuration is axisymmetric about the x axis, therefore, we can use a spherical coordinate system in which r is the distance from the particle center to a location in the fluid, theta is the azimuthal angle. There is a third meridional angle, of course, but there is no variation in that direction. Okay. And therefore, the equation for the temperature field was of the form V r partial T by partial r plus V theta by r partial T by partial theta. Okay. Recall that in this particular case, r is the cross stream direction and theta is the streamwise direction, okay, because the velocity field you would expect at the surface, okay, the velocity field, okay, to be in the theta direction along the surface. Okay. Therefore, theta is the streamwise direction, r is the cross stream direction. In the last lecture, I had justified for you that streamwise diffusion can be neglected in comparison to cross stream diffusion in this particular case, okay, where the thickness of the boundary layer is much smaller than the particle radius. You can neglect streamwise diffusion in comparison to cross stream diffusion, and there is a balance between convection and cross stream diffusion. Okay. So, therefore, this just becomes alpha. Okay. In a spherical coordinate system, there is only cross stream diffusion in the r direction. So, this is 1 by r square d by dr of r square partial t by partial r. Okay. And then we had done the scalings, okay, V r star is equal to V r by V free stream velocity, V theta star is equal to V theta by V f s, T star is equal to T minus T infinity by T naught minus T infinity, and the radius r star is equal to r by r. And as you recall, we had some rather complicated expressions for V r and V theta. In the boundary layer, the distance from the surface is much smaller than the radius of the particle. And in that case, we can expand out the velocity fields in the small parameter, which is the distance from the surface. Okay. If you recall, we had expressed the r coordinate, okay, as r star is equal to 1. Okay. R star is equal to 1 is the surface, okay, or r is equal to capital R is the surface of the sphere. When you go a small distance away from the surface, I can write this as 1 plus delta star into eta, okay, where delta star is the scaled boundary layer thickness. Okay, delta star is the scaled boundary layer thickness scaled by the radius r, and eta is a similarity variable. Okay. Eta is a similarity variable. Delta star decreases to 0 as the Peclet number becomes larger and larger. As the Peclet number becomes larger, the heat that is diffusing from the surface gets rapidly convected downstream with a higher velocity. Therefore, the disturbance to the temperature is restricted to a thinner and thinner layer close to the surface. So, delta star decreases as the distance decreases, as the Peclet number increases, I am sorry. Eta is order 1 in the boundary layer. Okay. It continues to remain finite in the limit as the Peclet number goes to 0. Okay. So, this gives us the definition for eta, okay, is equal to r star minus 1 by delta star. Okay. So, that is the definition of eta. This delta star is a function of the streamwise coordinate, which in this case is theta. In the case of a flat plate, if you recall, the streamwise coordinate was x. In this case, the streamwise coordinate is in the theta direction. We had substituted this into the expression for the velocity, okay, and we had got the scaled velocity as Vr star is equal to minus 3 by 2 cos theta delta star square eta square, okay, and V theta star (3 by 2) sin theta delta star eta star. Okay. So, these were the expressions for the velocity in the limit as delta goes to 0. Okay. In the limit as the boundary layer thickness goes to 0. We had simplified the expressions for the velocity which we had earlier, and we had got these expressions for the velocity. And these were substituted into the equation, if you recall. Okay. These were substituted into the conservation equation. Okay. And we had obtained an equation for the for the temperature profile as (3 by 4) PE into plus sin theta by 3 d delta cubed. D theta. Okay. Into minus eta square dt star, let me write that different color. This was the equation that we had got. In red are the temperature dependence on eta, and in blue is the boundary layer thickness dependent on dependence on theta. Okay. So, this was the expression that we had got. A similarity solution can be obtained only if the term in blue is a constant, and that constant can be set equal to 1 without loss of generality. Okay. And if we set that constant equal to 1, the solution for the temperature in terms of eta, the equation for the temperature in terms of eta just becomes minus eta square dt by d eta is equal to d square T and that can be solved with the boundary conditions. Okay. T is equal to T star as r goes to infinity implies that T star is equal to 0 far from the surface and T star is equal to 1 at the surface. Okay. T star is equal to 1. The scale temperature is 1 at the surface because T is equal to T naught as shown from here, and the scale temperature is 0 far from the surface. Okay. So, the disturbance due to the temperature is at the surface itself. Okay. So, subject to those boundary conditions, I can solve this to get the equation for the temperature profile. If you recall, this was 1 minus 3 per 2 by 3 by gamma of 1 by 3 integral 0 to eta eta prime e power minus eta prime cubed by 3. Okay, that was the temperature, that was a solution for the temperature profile. And the solution for the heat flux was at the surface was QR at R star is equal to 1, the radial heat flux at the surface. Okay. This is going to be equal to minus K partial T partial R at R star is equal to 1. Okay. Is equal to minus K into T naught minus T infinity by delta star, okay, dt star by d eta at eta is equal to 0. Okay. And this we had evaluated. Okay. This is equal to minus K into T naught minus, sorry, there is a plus sign here because the derivative is negative as is obvious from this expression here. The derivative is negative, so therefore you get minus K into T naught minus T infinity by delta star, which is a function of theta, into minus 3 power 2 by 3 by gamma of 1/3. Okay. This was the same solution that we had got for the heat transfer from a flat plate as well. Okay. So, the temperature in terms of eta turns out to be the same. The flux in terms of the boundary layer thickness turns out to be the same. Okay. So, this is equal to K into T naught minus T infinity by delta star. Okay. Now, we have to solve for this boundary layer thickness, delta is a function of theta. Okay. We have to solve for the boundary layer thickness, delta is a function of theta. Okay. The equation for this is 3 by 4 Pe into delta cubed cos theta plus sin theta by 3 d delta cubed by d theta is equal to 1. Okay. So, that is the equation for the boundary layer thickness, and we had solved this equation in order to get, okay, we had solved it, if you recall, using integrating factors. Okay, we had solved this equation using integrating factors to get delta cubed is equal to C by sin cube theta plus 2 theta minus sin of 2 theta by the Peclet number into sin cube theta. Okay, so, that was the solution for delta cubed, if you recall, in the last lecture. Okay. This was the solution that we had got using the integrating factor. Okay. The equation was reduced to d delta cubed by d theta plus 3 cos theta by sin theta is 4 by Pe sin theta. Okay. So, using the integrating factor, we had got this solution. As is obvious, this solution goes to infinity at theta equal to 0 because it is proportional to 1 over sin cube theta. Now, if you look at the second term here, okay, if you look at the second term here, okay, this second term is finite at theta is equal to 0. because limit as theta goes to 0 of 2 theta minus sine of 2 theta by sine cube theta. In the limit as theta goes to 0, you can use the expansion, that is sine of x is equal to x minus x cubed by 3 factorial plus x power 5 by 5 factorial plus etc. Okay. You can use that expansion, okay, for sine theta. Okay. So, this, if I use this expansion, this will be equal to limit as theta goes to 0 of 2 theta minus of 2 theta minus 2 theta whole cubed. Okay. And sine cube theta in this case goes as theta cubed. Okay. And you can see that these two terms actually cancel out. Okay. And this second term on the right goes to a finite limit in the limit as theta goes to 0. Okay. Therefore, I can make the boundary layer thickness finite at theta is equal to 0 just by setting this constant to 0, and then the boundary layer thickness becomes finite at theta is equal to 0. Okay. Recall that theta is equal to 0 is what we had referred to as the upstream stagnation point. Okay. This is where the flow is incident on the sphere and there is diffusion from the sphere. So, the diffusion from the sphere and the flow towards the sphere are in opposite directions, and at this location you would expect a balance between convection and diffusion and a finite boundary layer thickness as a result. Okay. You would expect the boundary layer thickness to be finite at this case. So, it is natural to consider the boundary layer thickness to be finite at theta is equal to 0 and adjust the constant here, so that the boundary layer thickness becomes finite at the upstream stagnation point. Okay. So, that sine theta is equal to 0 at the upstream stagnation point. Okay. Now, what happens at the downstream stagnation point? Okay. In this case, sine 2 theta, okay, if I just neglect this term here and I just include the second term, in the numerator sine 2 theta goes to 0, but at the downstream stagnation point, which corresponds to theta is equal to pi. Okay. The upstream stagnation point was at theta is equal to 0, because I was calculating the angle from the upstream stagnation point. Okay. So, upstream stagnation point will be at theta equal to 0, the downstream stagnation point will be at theta is equal to pi. Okay. At theta is equal to pi, this boundary layer thickness goes to infinity. That is because if you think about it, at the downstream stagnation point there is diffusion of heat from the surface. Okay. There is diffusion of heat from the surface, and the flow is also away from the surface at the downstream stagnation point. The flow is in this direction. Okay. And therefore, this combination of convection and diffusion, you would expect it to transport the mass downstream. Okay. Within a region that is called the wake. Okay. If you recall, we had discussed wake when we talked about flow past a sphere. In that case, it was the momentum wake, because we were calculating the velocity profiles. In this case, it is the wake for mass or heat diffusion, okay, which diverges close to the rear stagnation point, the downstream stagnation point. And here the boundary layer thickness actually goes to infinity. In order to find out the boundary layer thickness at this point, I have to rescale my theta coordinate to a thin region, okay, close to the downstream stagnation point. Okay. Turns out that this region is of thickness, okay, this region here is of thickness p power minus 1 by 4, okay, if you rescale it, okay, where there is a wake region in which the boundary layer thickness goes to infinity. It is not necessary to do this calculation, because the contribution to heat transfer from this region is actually small, and therefore, we can neglect the heat transfer from this region. Okay. So, it turns out that in order to calculate the correlation for heat transfer, we do not have to resolve the temperature field in this region. Okay. it is sufficient to just let the boundary layer thickness go to infinity. As the boundary layer thickness goes to infinity, the flux goes to 0, and therefore, this region does not contribute to the average flux, okay, from the surface of the sphere. Okay. So, this is the expression for the boundary layer thickness. Delta star is equal to 2 theta minus sine of 2 theta by P e power 1/3 sine theta. Okay. This whole thing to the 1/3 power. You have to take this whole term to the 1/3 power. Okay. That is the expression for the boundary layer thickness. Okay. That is the expression for the boundary layer thickness. And now I have to substitute this into the equation for the flux here. Okay. I have to substitute this into the equation for the flux and calculate the average flux. Okay. So, for a sphere, the average flux is going to be equal to 1 over the surface area, okay, 4 pi r square, okay, integral, okay, of, okay, r d phi, the azimuthal angle from 0 to 2 pi, integral of r sin theta d theta, okay, from 0 to pi. Okay. Recall, in a spherical coordinate system, phi goes from 0 to 2 pi and theta goes from 0 to pi. Okay. Of this term here, okay, of this term here, okay, which will be k into T naught minus T infinity, okay, by delta of theta 3 power 2 by 3 by gamma of 1/3, okay, delta star. Okay. Kindly note a correction here. This should be r times delta star. Okay, this should be r times delta star, because delta star is a scaled distance which has been scaled by the radius. Okay. So, it should be an r times delta star here. Okay. And in this expression, the dependence on theta enters only through this 1 over delta term here. Okay. The dependence on theta enters only through this 1 over delta term, okay, here. Okay. So, there is no other contribution that depends upon theta. Okay. Integral over phi will just give me 2 pi. Okay. Integral over phi will just give me 2 pi. Okay. So, therefore, this will be equal to 1 by 2. Okay. The 4 pi and 2 pi will cancel out, the r square will cancel out, k into T naught minus T infinity by r, okay, into 3 power 2 by 3 by gamma of 1/3, okay, into integral 0 to pi, okay, sin theta d theta. Okay. Of 1 over the boundary layer thickness, which is this one here, okay, which is P e power 1/3 sin theta, okay, divided by 2 theta minus sin 2 theta whole power 1/3. Okay. So, that is the expression for the average flux. Okay. I can take some constants outside. This is equal to q average is equal to k into T naught minus T infinity P e power 1/3 by 2 r, okay, 3 power 2 by 3 by gamma of 1/3, integral 0 to pi of sin square theta d theta by 2 theta minus sin 2 theta. And I can use the trigonometric identity that sin square theta is equal to half of 1 minus cos 2 theta. Okay, use that trigonometric identity to simplify this expression. 1 by 2 integral 0 to pi of 1 minus cos of 2 theta d theta by 2 theta minus sine whole power 1/3. And I can simplify this expression by realizing that if u is equal to 2 theta minus sine of 2 theta, okay, then du, okay, is equal to 2 minus 2 cos of 2 theta, okay, is equal to 2 into 1 minus cos of 2 theta, okay, which is just equal to 2 times the numerator here. Okay. I should express this as so this is just du is just 1/2, the numerator of this expression is just 1/2 of du. Okay. So, I will get k into t naught minus t infinity p e power 1/3 by 2 r 3 power 2 by 3 by gamma of 1/3, okay, times 1 by 4 integral 0 to pi, okay, of du by u power half. Du by u power half is just going to be 2 times u power half, okay, in the integral of that 1 over u power minus half, the integral of du by u power half is equal to 2 u power half between 0 and pi. Sorry, this is u power 1/3. So, I should so this will be 3 by 2. Okay, evaluated between 0 and pi. Okay. So, the evaluation between 0 and pi of 2 theta power 2/3 is basically 2 pi power 2/3. Okay, it is basically 2 pi power 2/3 into 3 by 2 into 1 by 4 and all of those constants there. Okay. And you can evaluate all of these constants. Okay. You can evaluate all of these constants and you will get this is equal to k into t naught minus t infinity p e power 1/3 by r into 3 power 5 by 3, okay, into pi power 2 by 3 by 2 power 10 by 3 into gamma of 1 by 3. Okay. So, that is the final expression, okay, and you can evaluate this numerically. Okay. You can evaluate this numerically in order to get the final solution as is equal to 0.496 k into t naught minus t infinity into p e power 1/3 by r. Okay. And the Nusselt number is equal to Q average, it is scaled by k into T naught minus T infinity by the diameter, okay, not the radius. Okay. Classically, the Nusselt number is scaled by the diameter, not by the radius, and if you put that in, you will get the correlation as 0.992 P e power 1 by 3, okay, where the V free stream into the diameter by alpha. So, this is the correlation for the flow past a sphere. Okay. We have calculated it analytically using the boundary layer approximation and the fact that the velocity has to decrease to 0 at the surface. Since we are focusing on a thin region close to the surface, it is sufficient to consider the leading approximation for the velocity field in that region in an expansion in the small parameter delta. Okay. And once you do that, it is only a matter of finding the expression for the boundary layer thickness delta by solving this equation. Okay. One issue of physics that has to be understood here is that the boundary layer thickness, the constant in this expression, is determined from the condition that the boundary layer thickness is finite at the upstream stagnation point. It goes to infinity at the downstream stagnation point, because convection and diffusion are both away from the surface at the downstream stagnation point. Okay. However, we do not have to calculate the velocity, the temperature profile at the downstream stagnation point, because the contribution to the heat flux there is negligible. Okay. And based upon this, we have calculated what is the average flux and the Nusselt number correlation. How does this, how can this be extended for a general flow past a surface where the effect of the temperature disturbance is restricted to a thin region close to the surface? This I will discuss in the next lecture. I will see you then.